Okay, part 3, we get down to actual particle physics, where we start looking at some of the fundamental particles. And the first fundamental particle, the most important we're going to look at, is the lepton. Now, a lepton is not one of the participants in a leapfrog competition. Yes, I thought about that one before I started. It's a fundamental particle, meaning it has no internal structure. And the most important thing about it is it doesn't feel the strong nuclear force, doesn't feel it, not bothered by it, doesn't feel it. And the second most important thing is that it's basically an electron to all intents and purposes. There are other ones, but the electron is the most important lepton. So it's a fundamental particle, about 2/1000 of the mass of a proton, so very light compared with the proton. Doesn't feel the strong nuclear force, which I've put in a different colour. That's how important it is. Now, the matter particles are mostly electrons, but there's also muons and tau. And we also have an antimatter components of positrons, anti-tau, anti-muons. Now, antimatter was first suggested by the cat down in the bottom right-hand corner, Paul Dirac, him of the many children and somewhere on the spectrum sort of thing. I don't know if you remember the famous story I told about him, which was that Einstein once put his hand up in a lecture Paul Dirac was giving and saying, "I don't understand that equation." And Dirac just ignored him and went on. And at the end they said, you were kind of rude to Albert. And they said, "Why was I rude?" He said, "Well, he asked a question." He said, "No, he didn't. He made a statement. He didn't understand the formula." Well, that's kind of Paul Dirac all over, that was. And if you see him interviewed in later life in the 60s, he made quite a few documentaries with the assistance of his missus. And he is one, he's one out there, dude. Anyway, so Paul Dirac, he was the first person to come up with the idea that if there was a plus, i.e. there was matter, there must be a minus, antimatter. And he was right. So this is it. This is the first proof of the idea of antimatter. At the top you have a positron, which is a positive equivalent of the electron. It's antimatter equivalent. Meeting an electron and disappearing into a piece of energy, electromagnetic radiation in this case. Well, in most cases, in all cases we think. Basically, it's called annihilation. This is the combination of two bits of mass to turn into energy. Oh no! Energy is being created out of nothing. Oh, that can't be true. We learnt that at junior cert. So how does annihilation actually work? Well, basically, a positron, that's a positron, and an electron, that's an electron, meet in some way, physically meet, I'm talking about, and form two gamma waves, two photons of electromagnetic radiation. Now it's two in order to conserve momentum. Not entirely the way we understand momentum in terms of linear momentum, but it's momentum generally. And momentum is conserved. There's momentum before in that the two particles, the electron and the positron, have momentum, and it has to be carried away somehow. And it's carried away because there are two gamma waves. And if you say, it's a wave, it can't have momentum because it hasn't got any mass, then you really don't understand how complicated physics is or anything about duality, which you don't at this stage, so don't worry about it. You just have to say there are two photons produced because it conserves momentum. Now, what does all this mean in terms of energy? Well, it means that the mass lost by these two particles here turns into the energy of these waves. So the energy created is given by E equals mc squared. You work out the mass of the two particles, you turn them into energy in form of joules, and then you turn that energy into frequency using Planck's law. There's Planck's law at the bottom, E equals hf. Now the 2 there is obviously there because there are two. I know I've emphasised this a few times. There are two electromagnetic waves, two photons of energy, which will have the same frequency but travel in opposite directions to conserve momentum. Matter turns into energy. So I did the actual calculation here for a proton and an antiproton. Annihilation, which has been observed. This is the atomic mass unit mass of a proton. And if you notice, the antiproton has exactly the same mass. So we just get 2 times it. So we turn that mass into energy when a proton meets an antiproton. Now, because there's a great deal more mass, there's a great deal more energy when a proton meets an antiproton. why we can't use its energy is we don't know something is an antiproton. We can't spot it until it joins with a proton and annihilates. We can't collect together antimatter. We can't put it in one place so it can combine with energy in any large quantities. So this is the mass which is lost in terms of atomic mass units. Now you will be able to convert that into kilograms using this formula here, because this number is in the logbook. It's in the logbook. And what happens, you see, is you look it up in the logbook. It's written down in the logbook, somewhere around the 40s. I forget which page exactly, but you can find it. It's where all the units are, the mass of the proton, things like that. And it says 1 atomic mass unit equals 1.66 times 10 to the minus 27 kilograms. And you use that, that's the conversion factor, you see. You multiply your atomic mass units by your conversion factor and you get a mass in kilograms. And you in kilograms, because it's got to be kilograms, is the m in equals mc squared. They have to be kilograms. You multiply that, of course, by the speed of light squared. 3 times 10 to the 8 squared is 9 times 10 to the 16. You use a calculator, obviously, times that by that, and you get a number of joules. A small amount of joules, I'll grant you, 10 to the minus 10, is not going to even light a light bulb. It's not going to power an ant. It's not going to power an ant to pick up even the smallest grain of rice that can possibly be conceived. No. But you've got to remember that although each individual action has a small amount of energy, it's the sheer number of actions which are possible. You just have to compare everything to Avogadro's number, the number of particles there are, number of protons there are in 1 gram of hydrogen. And that's 6 times 10 to the 23. That's a lot of particles. So if you multiply those two numbers together, you'd have enough energy to blast a hole in the earth. So all you have to do is get rid of a whole bunch of hydrogen, like a gram, and, wow, enormous amounts of energy. And this is essentially, of course, how the fusion and fission bombs work. Not by getting rid of a whole particle, but, you know, getting rid of binding energy. So, in order to turn the energy you've just worked out, which I hope by now you can do, E equals mc squared, difference in mass, that kind of thing. In order to find out the frequency of the waves which are produced, we use Planck's law. Now, if you think I look a bit like a geeky bald Jew, then you've got to look at pictures of Planck. He just takes the biscuit. Really, you'd be pointing at him down the street. He is the weird looking guy. He could have played Gollum without any makeup. Anyway, he's brilliant physicist, great friend of Einstein. He came up with the idea that energy comes in packages called photons, and he came up with this law, E equals hf. He didn't call it Planck's law and Planck's constant. We did that after his death as a mark of tribute. He was far too modest a man for that kind of thing. So what basically it says is if you have an amount of energy, you can find out a frequency. And if you have a frequency, you can find out the amount of energy of that photon, of a piece of electromagnetic radiation. So here is the energy which has been created. And all that energy is passed on to exactly two electromagnetic waves, electromagnetic radiations. So photons of such. So we simply put in our energy. We put in Planck's constant, we work out F by division. Now that has to be then divided by 2 because there were 2 waves leaving the site of the annihilation. So we divide that by 2 and we get the frequency of 1, which is still very, very high in the high energy gamma range. That's kind of very high energy gamma waves with that sort of a frequency. Now in practice you actually get a bigger frequency than that because you've got more energy to dispose of, because as well as the mass being lost, you've also lost the kinetic energy of the two particles. The positron and the electron hit each other at some velocity, and that kinetic energy that they possess at that moment also has to be converted into the energy of these two electromagnetic photons, these two waves of energy. Okay, so that also has to be accounted for, so it actually gets bigger than that. Right, now, this may look like the same picture, it's just a very similar picture. This was in the same project, taken in the same thing. People thought it was also an annihilation, until later on people said, no, that can't be annihilation, it's the wrong way around. If it was an annihilation, it would go the other way. And then people said, oh, it is a bit, what's happening? Pair production. Even weirder than annihilation is pair production. Suddenly, presumably an electromagnetic wave, we have no idea, but how else could it possibly happen, turns into a positron and an electron. Now, I have made these wrong. I've kind of done it on purpose, accidentally on purpose. I'll talk about it in a moment. Basically, what you're looking at is a positron and an electron being created from energy. So it's the opposite of annihilation. It's called pair production. And of course, you do the calculation in the opposite as well. You work out the frequency of the wave. That tells you how much energy you've got, and that energy gets converted into mass. It's quite easy. However, you can no longer write the electron down like this. You're supposed to write the electron down as 0 minus 1 and the positron as 0 plus 1, like that. This positive and negative, you see it in textbooks, you shouldn't write it down like that anymore. That's the way you should write it. Okay, now, of course, physics being physics, nothing ever stays simple for very long. Very shortly afterwards, they worked out that as well as annihilation, you had annihilation production, which is where a pair of protons will annihilate each other. A proton and an antiproton will annihilate each other, and then a moment later they'll form again, travelling at a slower speed. And the loss of kinetic energy is turned into matter. This is what we're doing at CERN. We're bashing things together so hard that when they re-emerge at a slower speed, that the energy of their kinetic energy is getting turned into mass. Now, and this is a very common process. These are producing 3 mesons called pions. And we'll talk about what a pion is in the next section. But it's producing 3 completely new particles just formed out of the kinetic energy of the proton and the antiproton as they hit each other. Now, CERN can produce that much energy, 4 gigaelectron volts. Now, an electron volt is simply the amount of voltage that you've passed it through times the charge on the electron. So basically, you're looking at that many joules. You multiply your 4 giga, G means 10 to the 9. Anyway, G means 10 to the 9. So 4 gigaelectron volts times the charge on the electron, a very important quantity. The charge on the electron, there it is, and you get the amount of energy produced. Now look how similar that is. Very similar size in joules. Now, 3 pions, you can work out how much energy it takes to produce 3 pions using E equals mc squared, because you've got 3 pions. That's the mass of the pion. You have to look that up. And that's how much energy. So if they crash into each other, they produce 6 times 10 to the minus 10 joules, but you only need 6.7 times 10 to the minus 11 joules to produce those 3 pions. So you can actually produce 4 times as many as that. You can produce like 12, I think, pions from such a crash, and still have the protons have enough energy to leave the site, and the pions as well. It's an amazing amount of particles you can make by just crashing together 2 protons. The pions are lighter, but not that much lighter, and it's just this incredible amount of energy we can generate at CERN that we can create all these new particles literally out of the kinetic energy of their combatants. Right, this is a very good question for you to attempt. It's got all the basic bits, calculations, and it's even got a picture of Dirac. There can't be that many pictures of Dirac, because every time I see a picture of Dirac, it's the same picture. I think it must be from his Nobel Prize. Maybe that's why it's there. And they all have a picture taken for the Nobel Prize, and that's him staring off into space looking intelligent. I wish someone took a picture of that like me, but then I never look intelligent.